Hello dear students, welcome you all. In this lecture, I am going to discuss about the Bose-Einstein distribution law. Clear? Bose-Einstein distribution law. Clear? Bose-Einstein distribution law is basically the first step to go into the Bose-Einstein statistics. First of all, we have to understand what is Bose-Einstein statistics. So we know very well that Bose-Einstein statistics basically are quantum statistics. Quantum statistics. Clear? In quantum statistics, there are two branches: Bose-Einstein and Fermi-Dirac statistics. So this is Bose-Einstein statistics. We know that Bose-Einstein statistics was developed by S.N. Bose and Albert Einstein in 1924-25. Clear? SN means Satyendra Nath Bose, who was an Indian, and Albert Einstein. So SN Bose and Albert Einstein have uh, studied the behavior of bosons in detail, and their results are collectively known as Bose-Einstein statistics, right? So the one thing that we should be clear that this statistics is applicable to the bosons. Bosons means those particles which obey Bose-Einstein statistics. This name is given to this statistics according to this statistics. Bose-Einstein makes bosons. Clear? So which type of particle these bosons are? We know very well that bosons are those particles which have either zero or integral spin. Clear? So these are the particle of this category. These are photons, examples, graviton, mesons, right, etc. So all these particles are bosons. They come under this category. Clear? Bosons or category, and they obey Bose-Einstein statistics. Clear? So this is about the Bose-Einstein statistics. Now here we are going to drive a Bose-Einstein distribution law. So what is the need of that law? Right? We have developed this law in the case of Maxwell, Boltzmann statistics also. And we know that this law, distribution law, tell us about the Ni upon Gi, means it tell us about the this factor, ratio of the number of particle into a particular compartment to the number of cells in that compartment in terms of energy. Clear? Or it tell us that on what factors this Ni upon Gi depend, right? So we will develop a similar kind of law that we develop for Maxwell Boltzmann statistics here in case of Bose-Einstein statistics, right? So to do so, let's consider we have n bosons, small n, right? We have small n bosons. Clear? Now, before going into all this discussion, we have to make some assumptions, right? The first one is that all these bosons are identical and indistinguishable. Clear? This is the first one. Right? And this is the main thing that differentiate quantum statistics from classical statistics. In quantum, the particles are identical as well as indistinguishable. This is the one thing. Other thing is, in case of Bose-Einstein statistics, the minimum volume of a cell in phase space is it is equal to h cube. Here h is a Planck's constant. Clear? We know very well. Now we can't go below this limit in quantum statistics. In classical statistics, it was possible to consider the value of the volume of the phase space cell as low as possible. But here in quantum, this is the limit. Clear? We can't go beyond this. Clear? The third, this was the second thing. This was the first. Clear? The third thing that we have to keep in mind is here, there is no restriction on the number of particle entering in any compartment or any cell. Clear? Any number of particle can enter into any cell. Clear? Means this statistics is not going to obey Pauli's exclusion principle. We know very well that bosons do not obey Pauli's exclusion principle. It is obeyed only by the fermions. Clear? So there is no restriction. So these are some assumptions that we have to take in mind before proceeding further for developing a distribution law. Right. Now I am considering a space that is given to us in which we are going to distribute these n particles. Like this is the given space. I divided this given space into different compartments of different number of compartments in of different size. Clear? This is the first compartment. This is the second one. This is the third one. This is the fourth one. All these are of different size. Clear? You can see here fifth one. Similarly, this is sixth one, and so on. This is the kth compartment. Clear? This is k minus 1. Clear? So all these compartments are numbered as compartment number 1, compartment number 2, compartment number 3, compartment number 4, compartment number 5, compartment number 6, compartment number k minus 1, and this is a k. Clear? So I divided the given space into different compartments. Clear? What is the next step? Now I'm going to divide all these compartments into very small cells of equal size. Clear? So let in the first compartment, this is the first cell, this is the second, this is the third, this is the fourth. All they are these cells are of same size. Clear? Right. So what I did, I divided all these. I'm going to further do it. So you can see here. Right. So now let in the first compartment there are a Z1 number of cells. Similarly, in the second we have a Z2 number of cells. Clear? Z1 in the second we have a G2, in the third we have a G3. Similarly, this is G4, this is G5, this is G6, this is Gk minus 1, this is so now the available space, clear, that is divided into different compartments, and then all these compartments are further divided into small cells of equal size, so that first compartment has G1, second has G2, and so on. Kth compartment has a GK number of cells, right? Now we are going to distribute these n, small n was the total number of particles or bosons in this particular case. We have to divide or distribute these particles in all these compartments and then ultimately into these cells, right? So there are different possibilities. Different number of particle can go into different compartment, right? So there are large number of possibility. We are considering one possibility among those possibilities, right? I can say we are considering one macro state. Clear? In that macro state, the first compartment has a N1 particle, second has a N2 particle, third has a N3, similarly fourth has a N4 and a N6, N5, Nk minus 1 and Nk. So I consider this macro state N1, N2, so on, Nk. This is the one possibility, means N1 particle in first compartment, N2 in second. So I consider this, right? Now I am going to find out the distribution of different ways of distribution of these particles in these total cells. So for it, I will start with the first compartment. So I'm considering now the first compartment only. So first compartment means we are only considering this. Clear? So if we look at the first compartment, then in first compartments, number of particles is not dark, changing the color. Number of particles is equal to N1. Clear? Number of cells is equal to Z1. Clear? So this is the given condition for the first compartment. Clear? Now we have to find out the total number of meaningful arrangements of these N1 particle in Z1 cells. Clear? This is the task. We will find out the meaningful arrangements for the first compartment, then we will apply that result to the all compartments. So it will give us the total number of meaningful arrangements for this given macro state. Clear? Now to find out the number of meaningful arrangements, clear, in the first compartment. Clear? How we can find that? Now the particles are identical and indistinguishable. So for doing so, I consider 7 particles. I give them name as 1, 2, 3, 4, 5, 6, 7 for my convenience. Clear? Let this is first, second, third, fourth particle, fifth, sixth, seventh. Let N1 is equal to 7. Clear? Now these are 7 particles, right? Now let I make 4 partitions. Okay. So 4 partition means 1, 2, 3 and 4. Clear? So what I did, I took 7 particle. This is now first, I can say first cell. This is the second cell. This is the third cell, and this is the fourth cell. Clear? So you can see here, I have 4 different cells and I have 7 different particles. Clear? Now look at this picture. Clear? If now I change the position of any of this partition. Clear? How many bars are used for creating these partitions? 3. So I'm changing the partition. That this is taken to the this position now. Now again, you can see here, now in the second cell, I have these particles. In third, I have these 2 and this. So this is the way. Now this is first, second, third and fourth. So I can do all these things in how many ways? Clear? I can do all these things in how many? 1, 2, 3. 3 factorial ways. Okay? Means I can make different compartments. Size, matlab, if I make it in the simple words, I can make different compartments by adjusting these partitions. Clear? So, and I can do it in 3 factorial ways. Clear? So, this is the way of changing the size. Clear? Now, each arrangement is different. Earlier it was different. Now, the number of particles 1, 2, 3, 4, 5, 6, 7. Now, it can be like this. It can be like this. 7, 6, 5, 4, 3, 2, 1. It can be the possibility. Possibility can be 6, 5, 3, 4, 1, 2, 7. It can be the possibility. So it means 7 factorial possibilities are also there. Clear? Base. So if I consider both the factors, number of particle plus number of ways of creating the partitions here. So it means now this is equal to 7 plus 3 factorial. Now what is 3? 3 is basically 1, 2, 3, 4. 4 minus 1 means number of cells minus 1. So this is 7 plus 4 minus 1 whole term factorial. So this is the total number of a way. Clear? Of arranging these 7 particles in these 4 different partitions. Now, as we have 7 particles and we have 4 different compartments. So this is our choice from which compartment we will start. We can start from this compartment also. This is another possibility. I can start from this compartment. Which compartment will lead this array, this distribution? So this can be done in how many ways? This can be done in 4 ways. Clear? 1, 2, 3, 4. So the total number of ways of arranging these 7 particles in these 4 different compartments is equal to this. Clear? Now this was the case of an example. If I make it journal result, then it will become Z1 into N1 plus Z1 minus 1 whole term factorial. So this is what? This is the total number of arrangements of N1 particle in Z1 cells for the first compartment. Clear? So I have now wrote the total number of arrangements. Clear? This is what? Total number of arrangements. Right. Now look at this picture. Here it is 3, 4. If it becomes 4, 3. If it becomes 4, 3. Is it meaningful or meaningless? 4, 3. If it becomes 6, 5. Now as I have give them name for my convenience. These particles are identical as well as indistinguishable. So 3, 4, 4, 3 means the same. It means all these arrangements are meaningless. It means 7 factorial ways of arranging these particles among themselves are meaningless. Because here are 7 particles, so 7 factorial. So all these arrangements are meaningless. Similarly, we have 4 compartments. So arranging these compartments among themselves is again meaningless. So total number of meaningless arrangements n 1 factorial into g1 factorial. So this is what n1 factorial into g1 factorial is. I can say total number of meaningless arrangements. Clear? That is equal to n1 factorial into g1 factorial. So now I'm going to write down the total number of meaningful arrangement. That is equal to, we know total arrangements, that is g1 into n1 plus g1 minus 1 factorial divided by This is total arrangement divided by meaningless arrangements. N1 factorial into G1 factorial. Clear? So this is the case of first compartments, right? So I can even simplify it. It is G1, so I can write it G1 into G1 minus 1 factorial. So it will get cancelled out. So then I will be left with the N1 plus G1 minus 1 factorial divided by N1 factorial into G1 minus 1 factorial. So this is what? This is the total number of meaningful arrangements for the first compartment. Clear? First compartment. So we will get the same type of results for the other compartments also. For the second compartment, here it will come to N2, Z2, N2, Z2. Same thing, kth compartment, NK, ZK, NK, ZK. So we will have all these different number of meaningful arrangements for all these compartments. So if I want to find the total number of meaningful arrangements for this whole space, right? Then what I have to do, I have to write that is W N1, N2, N3, so on, Nk, right? It is equal to W is what? Total number of meaningful arrangements for this macro state, and this is called thermodynamic probability, right? So this is equal to what? N1 plus G1 minus 1 factorial divided by N1 factorial into G1 minus 1 factorial multiply N2 plus G2 minus 1 factorial N2 factorial into G2 minus 1 factorial into so on Nk plus Gk minus 1 factorial divided by Nk factorial into Gk minus 1 factorial. So this is what I got when I considered all the compartments. Obviously, all the cases will get multiplied. So then I can write in this way multiplication symbol. I go from 1 to k Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So I converted it into the multiplication. Clear? I simply write it now W. Clear? Stands for thermodynamic probability. Now taking log on both the sides, natural logarithm. So log E W is equal to log E Ni plus Gi minus 1 factorial minus log of Ni factorial minus log of E Gi minus 1 factorial. Clear? So now this is the next step. When I took the log on both the sides, as Ni and Gi both are big numbers, so now I'm going to use the Stirling formula. Clear? So according to Stirling formula, log of n factorial is equal to n log of n minus n, right? So it is going to be applied in all these three relations. So when I will apply it here, it will become Ni plus Gi minus 1 log of Ni plus Gi minus 1 n log n minus Ni plus Gi minus 1. Clear? Minus Ni log of Ni Now here it is negative sign, so I am taking minus n log n minus ni, right? Again, I am taking this term in the here minus bracket zi minus 1 log of zi minus 1 minus zi minus clear. So this is the expansion. So now I'm going to simplify it. So I will expand these brackets. So it is ni plus zi minus 1 log of ni plus gi minus 1 minus ni minus gi plus 1 minus ni log of ni plus ni minus gi minus 1 log of gi minus 1 minus minus plus plus gi minus 1. Clear? So now it becomes this after expanding. So some terms gi cancelled, ni cancelled, 1 to 1 cancelled. So now here we know both ni as well as gi are very large as compared to 1. So I can drop 1 from here, 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 all these factors, right? So then when I will drop all these factors, then it will give me clear. uh, One thing that I forget here, that when I took log on both the sides, then it will become a summation. Clear? So it is I goes from 1 to k. Clear? So then in that case, it will become summation of ni plus zi bracket log of ni plus zi minus ni log of ni minus zi log of zi. Clear? So this is what I got when I simplified it by applying this condition. Clear? Now this is equal to log e w. Clear? Now taking differentiation both the sides means taking d log ew on both the sides here also, but keeping in mind that zi is equal to constant. Clear? So when you will take the differentiation, so it will become uh, dni differentiation of first factor dni log of e ni plus zi, right, plus ni plus zi into differentiation of second, that is 1 upon ni plus zi log differentiation of log into dni. This is the first. Similarly, for the second term, I will have minus dni. Now minus is there, so I took it here. Minus dni log of ni plus ni into 1 upon ni into dni. Here. This is the first term and this is for second term. For this term, it is equal to 0 because we have considered gi is equal to constant. So the things get cancelled. So after simplification, I got dni log of e ni plus zi plus dni, clear, minus d dni log of ni, clear, and minus dni, clear. So this is what I got when I rearrange this equation. Then after next step, so it becomes this get cancelled, So it becomes in the next step uh, d log of e w is equal to summation was also there, summation I go from 1 to k log of e ni plus zi minus log of ni bracket into dni. Let this is equation number clear. Now we know for the equilibrium state, for the most probable state, W is equal to W maximum, right? So in that situation, D log EW should be equal to 0. D log EW should be equal to 0 under this condition. So now I'm applying it here. So it means this equation number 1, that should be equal to 0. So I can write here this is equal to 0. Clear? Now this is the equation. Let this is equation number 2. Now I'm going to apply two constraints on the system that we have assumed in the beginning. Clear? The first one is we know in this case as n is equal to n1 plus n2 plus n3 so on nk. Clear? So this is the total number of particle. Clear? So here, as the total number of particle is constant, so it means summation of ni. I go from 1 to k is equal to constant. Clear? It means dni summation should be equal to 0 because the total number of particles, the sum of all these particles is equal to n and this is constant. So this is equal to 0. This is the first condition. The second condition is the total energy of the system is also constant. So it means E is equal to N1 E1 plus N2 E2, that is so on Nk Ek. Clear? That is also constant. It means summation of Ei Ni is also constant. It means summation of Ei Dni, when I took the D, that should be equal to 0. So these are now two conditions. Clear? This is the first one and this is the second one. This is, I gave it name. This is equation number 3 and equation number 4. Now I'm going to multiply it with alpha and this with the beta. And then I'm going to subtract these two equations from this equation. Clear? So when I will do it, I will get summation of same as it is log of E ni plus zi minus log of ni dni minus alpha summation of dni minus beta summation of ei dni, that is equal to 0. I put all these things here in equation number 2. So when I will rearrange it, simplify it, I will get summation log of E ni plus zi upon ni, clear, minus alpha minus beta ei into dni, that is equal to 0. Clear? I simplified and here it is negative, so I took it in the denominator. dni is common in all the terms, so it is here I goes from 1 to k. Now as dni are independent of each other, so this cannot be equal to 0. It means this term inside the bracket must be equal to 0. So I can write, I can say this this should be equal to 0. Clear? So right here it is alpha, right? So now I can simplify this equation. Log of E Ni plus Gi upon Ni bracket clear is equal to alpha plus beta E I. So when I will simplify this equation, I will get, you can do it, Ni upon Gi is equal to 1 upon e raised to power alpha plus beta ei minus 1. Clear? So this is the required distribution law that I told in the beginning. Now this distribution law is telling us about the ratio of the number of particle in ith compartment to the number of cells in terms of energy of that compartment. Clear? Ni upon Gi is equal to 1 upon e raised to power alpha plus beta ei minus 1. Now, what is the difference between this law and the law of Maxwell-Boltzmann distribution? The difference was, in that case, we have only 1 upon e raised to power alpha plus beta ei. So here, negative 1 minus 1 factor is induced in the denominator. Clear? Uh, you can put the value of beta. We have derived it in that case. It is 1 upon kt. Clear? So if you put that value, then this equation will become Ni upon Gi is equal to 1 upon e raised to power alpha plus Ei upon kt minus 1. Clear? So this is the distribution law. Right? This is very, very important in all the applications of Bose-Einstein statistics. We will start from this Bose-Einstein distribution law. Bose-Einstein distribution law. Clear? So we have to memorize it. For the Maxwell-Boltzmann statistics, it was this. For Bose-Einstein statistics, it is this. We will see in the coming lectures that in Fermi-Dirac statistics, it will become plus in case of Fermi-Dirac statistics. Means here, in that case, we will have a plus 1 in the denominator. So this is all about this distribution law. We have derived it by considering n indistinguishable identical bosons and then distribute them in different compartments, and then after we arrived this result. Right. So thank you very much.